Flipped classroom video for Further Maths Unit 2, Contingency Tables with chi-squared. Sometimes you are interested in the frequencies with which two criteria are fulfilled at the same time. In a contingency table, individuals are classified according to two different attributes, and the number of individuals, i.e. the frequency, satisfying both, are shown in the appropriate cell in the table. We are interested in whether there is any association between the two sets of results, and we would set up the following hypotheses. The null hypothesis would be that there's no association between the attributes, that they are independent of each other, and the alternative would be that there is association between the attributes, that they're not independent. So, our first example, during the trial of a new drug, 60 volunteers out of 200 were tested with the drug. Those experiencing a relief of their symptoms and those who did not were recorded as follows. So use a suitable test to see if there is any association between the treatment with the drug and the relief of the symptoms. Use a 5% significance level. So we are given, these are the observed values, the results in the tables with the totals along the bottom and down the side. Our hypothesis, there is no association between being treated and having relief. They are not independent. Against, there is association between being treated and relief. They are not independent. Okay, so we need to work out the probability of each cell. So being treated and having relief. So being treated would be 60 out of the 200 and having relief would be 50 out of the 200. And then we multiply that with the frequency to get our expected value for being treated and having relief. So that comes to 15. Doing the same with others. So being treated would be the 60 out of the 200 and no relief would be 150 out of the 200 and multiply by 200. So one of the 200s cancel and we're left with 45. Having relief and not being treated. So having relief and not being treated is 140 and 50. So 50 out of 200, 140 out of 200, multiply by 200 gives us 35. Not having relief and not being treated, so would be 150 and 140 respectively, and then we get the value 105. So our expected value for each cell should be those. We need to set up our test statistic. So we need the observed value minus the expected value, square that and divide by the expected value. So for each cell, I've got 10 minus 15 squared divided by 15 for the first one. 50 minus 45 squared divided by 45 and so on. And for our test statistics for these results, I get 3.175. So looking up the degrees of freedom, because we've got we've got rows and columns to contend with, we do not need to calculate the last value with each row because the sum has to equal the row total, and similarly we have the last value in each column is fixed as well. So our degrees of freedom is the rows minus 1 multiplied by the columns minus 1. So in our situation, table 6, as in the last video, 5% they wanted, the tail end, 2 rows, 2 columns, they have a 2 minus 1, 2 minus 1, 1 is our value for the degree of freedom. So we are looking at 3.841 as our critical value. So the critical level would be that chi-squared is greater than 3.841. Our value is not, our test statistic is not within this region, so we are keeping H0. The treatment and relief felt are not associated. Another example, the grades of 200 students in both Maths and English were studied with the following results. Use a 0.05 for significance level, that's 5%. Test these results to see if there is an association between Maths and English results. State your conclusions. So our hypothesis, there is no association between Maths and English grades, they are independent. Against, there is association between Maths and English grades, that they are not independent. So our observed value, so English with A, English with B, English with C, Maths with A, B and C, and our totals now at the side. So Maths A grades have got 63, Maths B grade 99, Maths C grade 38, English A grade 67, English B grade and English C grade, giving us a total of 200 students. So those are the observed values. Then our expected values, so the frequency of Maths with A and Maths with English would be 63 out of 200 multiplied by 67 out of 200 multiplied with a frequency of 200. So those are the two probabilities multiplied by the frequency 200, giving us 21.105 as the expected frequency of Maths grade A and English grade A. So we can see the one of those 200s cancels. So the Maths grade A with English grade B is 63 and 85 out of the 200. So one of the 200s is cancelled, giving us 26.775. And Maths grade A with English grade C, so 63 multiplied by 48 divided by the 200 gives us 15.12. The others, Maths grade B with English A, gives us that. Maths B with English B, Maths C with English, Maths B with English C, and then the Maths C with each of the English grades. So we've worked out all those expected values. Don't round up too early. So there's our observed values. There's our expected values. We need to work out the test statistics as the observed minus the expected squared divided by the expected and add them all up, and we get 8.57. Be careful with these calculations. 8.57. We're looking at table 6 again, 5% tail end. We've got 3 rows and 3 columns, so 3 take away 3 multiply by 3 take away 3. So we have 4 degrees of freedom. Looking up table 6, 4 degrees of freedom, 5% tail end gives us 0.95. So our critical value is 9.488. Our critical region is above that. Our test statistic is not within that. Therefore, English and Maths marks are independent. We're keeping H0. An exam type question. A random sample of 100 people were asked if their finances were worse, the same, or better than this time last year. The sample was split according to their annual income, and the results are shown in the table below. To test at the 5% significance level whether or not the relative state of their finances is independent of their income range. State your hypothesis and show you're working clearly. So our hypothesis, there is no association between the relative state of their finances. Again, that there is association. They're not independent. So our observed values and totals. Worse, same, better, and now totals. So less than £15,000, we've got 34 in the sample, and greater than 15,000 we have 66. Worse, same, better. So we have those totals. Need to work out the totals before we carry on. Then our frequency for each table. So worse and less than 15,000 is the probability multiplied by the 100. So the probability of worse is 31 out of 100. The probability of less than 15,000 is 34 out of 100. We multiply by the frequency, so they will cancel, and we get 10.54 for the expected value of worse and less than 15,000. The other values come out to be, so worse and greater than 15,000. So worse is 31, greater than is 66, and we get 20.46. The same and less than 15,000, we get 10.54. The same and greater than 15,000, and better and less than 15,000, and better and greater than or equal to 15,000. So we get all those expected values. Remember, don't round up. So there's the table for expected values. We need to set up our test statistics. So each cell, the observed minus the expected, all squared divided by the expected, and we get those values, and our answer for the test statistic is 3.553. Comparing that with table 6, 5% again, tail end. Now we have 2 rows, 3 columns. So it's 2 take away 1 multiplied by 3 take away 1, which is 1 multiplied by 2, which is 2 is our degrees of freedom. And we get so 2 degrees of freedom, 0.95 tail end, 5% tail end gives us 0.95. So critical values, 5.991, a critical region is above that, chi-squared, that should be. So that it's insufficient, being as our value is not within that. There's insufficient evidence to reject H0. So we're keeping H0. There is no association between the state of finance and income. And that's the end of the video on contingency tables.